Yeah, just to recap a little bit. So I mean, we went through this. So we started with this, right, where this was the usual L2, and then we went through it, and then saw that the V can be replaced by the gradient, and then this formula can be interpreted as a geodesic distance on a Riemannian manifold, heuristically, and then we can derive the gradient and the gradient flow of the KL divergence with respect to this turns out to be the usual Fokker-Planck equations. And then, this in some sense here is a choice. Actually, like as we discussed in the break, all kinds of things could be considered here. But one thing that we discussed now was if we introduce this kind of matrix here, then we're not getting too far away from the usual Wasserstein picture. The main point is then that this Helmholtz decomposition changes and the M comes in here. And so the tangent space construction changes a little bit and the gradients change a little bit and the Fokker-Planck equation changes a little bit. And what happens is that the corresponding diffusion is some sort of preconditioned overdamped Langevin diffusion, and you can use this matrix M to, for example, counteract ill conditioning of the potential V. And this is, so for example, very much in the spirit of Girolami Calderhead. And in fact, this can be interpreted as in a Riemannian, in a geometric way. So, so what I want to say is that the inverse of this matrix M, it defines in coordinates a Riemannian tensor. And then this can be thought of as overdamped Langevin dynamics on a Riemannian manifold. So we just have to interpret everything in Riemannian ways. So we take the Riemannian gradient and we take Riemannian Brownian motion. So you have a manifold, you can have Brownian motion on the manifold, and the sort of the covariance of the Brownian motion is given in terms of the metric tensor. And then so sort of this equation is the same as this equation, or this equation is this equation in coordinates. And then this is a pretty canonical construction because you can say that we have a so we started here with this usual Benamou-Brunier, but pretty soon, of course, people figured out that there's nothing special really about RD, and you can do Riemannian, you can do Wasserstein distances on Riemannian manifolds, and this is precisely what you get then. Okay, and this is also, this is the Girolami Calderhead story that you do diffusion on the Riemannian manifold, so you get precisely to there. And the other thing is that here I said that M is allowed to depend on the point X, but in fact nothing at all has to be changed if we also allow dependence on the measure rho. Right, so we are free to, so we think of the space of probability distributions as a manifold, and we should define an inner product at a certain point, so which is a distribution. And so there's no problem at all letting this this scalar product depend on the point where we are at, because this is anyway the case in Riemannian geometry. And so it's allowed to depend on this. And so this way we can get still more intricate dynamics here. So for example, it makes sense to take here the covariance. So for M, we can take the covariance of rho. So it's a function from the space of measures into matrices. And this will give this Kalman story. So this then here instead of M, we get the covariance matrix. And the idea is that the dynamics is preconditioned by the covariance matrix of the dynamics. Yeah. So this is work of Frank and Andrew and friends. Yeah. And maybe the last example is we can, because this was also mentioned in the other talk, we can have here a reproducing kernel Hilbert space norm. So I'm not going to really say much about this. It's kind of easy if you, so we have to fix a positive definite kernel like this. And this induces a reproducing kernel Hilbert space with a corresponding norm. And if you don't know what that is, this can be written like that. Okay. So this can be written like this. Okay, this is not the usual way reproducing kernel Hilbert space norms are presented, because this looks more complicated than this. But for us, it's kind of good because so it involves the inverse, which we might have trouble defining, of this convolution type operator. But what is good about it is here before we had the M inverse, yeah, and we just saw that this comes in here with M as a matrix. And so this goes through. So we can have here, in terms of M, I just write this convolution type operator. It's just sort of the same algebra. We have to be a little bit careful for technical reasons, because this is a sort of a smaller space. We sort of intersect here. So here, then we've got the RKHS, and here we need to intersect. And here we take the closure in the RKHS, but it's not so important. These are just somehow technical details, right? But the important thing is that in the tangent space, somehow, as always, this shows up here. And so also here. And so the vectors that are somehow considered as pushing the density around in this kind of setting are given not by gradients, but sort of by convolved gradients. And then we go ahead, right? So here also instead of the T, instead of the M, so the same we put here this operator. So now we get the Fokker-Planck equation with this weird operator. And it's the evolution equation which describes Stein variation gradient descent as SVGT. So if we write an equation that describes this, then we get this. I don't know. I realized this was maybe a bit fast, but it's kind of.
So how would you use this? Like, how would you exploit this? Working on this Hilbert spaces.
Here, I mean, it's interesting. It gives a completely different. So it gives quite a different types of dynamics. So this is an interacting. Yeah, I wrote integrals, yeah.
Yeah.
But you can bring it into the interacting particle system by replacing by sums.
Yeah.
And it's an ODE, it's deterministic.
Okay.
Rather than stochastic.
Okay.
And you get you get a term that sort of drives particle away from each other, this one, and it's sort of in the same spirit as the Laplace operator in the diffusion setting. It's just that instead of noise, you use a deterministic drift between the particles. Mm-hmm. And it's sort of in spirit, it's similar, right? And then you've also got a gradient type term. And
so you can.
Yeah, it's just, I mean, maybe it has some advantages to use deterministic evolutions, and then also something that drives particles apart.
Yeah.
Yeah.
Okay.
So,
yeah. Cool.
But there's also, I mean, there's advantages and disadvantages, and I don't know. So, but yeah.
It's quite a nice example, I think, because you go from the thing where you have the precondition of the dependence on the position, but not the measure. And
Yeah.
the one that depends on the measure, but not the position.
Yeah. So here you can have. Yeah.
It's like even a step up from preconditioning. It's not just the same as putting a matrix in front of.
Yeah. I agree. Yeah. And it has a little bit of a different flavor, right? Somehow, because it's not really preconditioning that much.
I guess it's I guess the Kalman is kind of non-local in some way as well, but not in quite the same degree.
I mean, you're trying to achieve something a little bit different in the Kalman setting, right?
Yeah.
So, yeah. But still, algebraically, in some sense, I try to convey that this kind of there are strong parallels, at least.
Yeah.
In the Kalman one, you can take the precondition Euler, just make it on M being the covariance matrix of the particle, if that infinity, you discretize and get what these guys are.
Yeah. But I'm saying it's like it sort of is on its face local, but then it's non-local because the covariance is that.
Yeah.
There's the thing that Ben Leibler and his people did a little while ago, where it's kind of like you kind of do a localization kernel to just look at the covariance matrix of points near X. So,
Oh, I see. Okay.
So again, it's like semi-local.
Okay.
But
I wasn't aware of this work, but I mean, okay, there's a few things like this, right? I think.
Yeah. It's a stats and computing paper from 5-10 years.
Okay. Yeah.
Once you've defined this kind of alternative Einstein distance in the Bellamy-Brenier formulation, is there a way to recover some kind of analog of other formulations of Einstein distance?
So certainly it's difficult to recover the completely non-local one. It's possible to get to some sort of dual formulation. Yeah, maybe so. I don't know. What I will do now is, so I wanted to say a little bit about second order convexity and curvature and so on. I mean, I can't go into much detail, right? But I could sketch it a little bit, and this will show up then a little bit.
It seems like a good transition.
Yeah. Okay. Yeah. Unless there are questions more about this kind of stuff.
Just a quick one. Is there an SE version of the SVDP?
Yeah. So you can do. Right. You can take this M. Here you take kernels all over the place here. Like this is x1, then you have an identity matrix, and then here's x1, xn. This goes to xn and xn. So it's kind of interesting. So both SVG, so this is then exactly this form. With the M like this. It was interesting. So both this EKS and the Stein one have this form with particular choices for M. And what's interesting about this, when you take the limit as n goes to infinity, for the Kalman one, this disappears. So you're left with covariance matrix times the gradient plus noise. And for the Stein one, just because of the scaling and so on, the noise disappears. And so this ends up being this term, and the other term.
Just to clarify, so the limit is t doesn't go to infinity, it's just you said n.
And n goes to infinity. Yeah. So this is a finite n description because it's a weak form of the ODE. Yeah. Okay. Okay, yeah. So in some sense, it's interesting to go like Juan also said, like we want to try the best dynamics, right? We want to find the one that converges as fast as possible and so on, and it's difficult, of course, but we can try and understand so maybe there's a point in asking what kind of geometry we should put here to make it fast, something like this. And like this whole autocalculus, I mean, the reason why Otto became famous for this is that you can go also beyond this first order. So here we only did first order derivatives, right? But the thing becomes much more interesting, and so on if you do second order derivatives. Because it's like always, it becomes more interesting when you do second order derivatives, I guess. And it's connected to what Sam was talking about, because second order derivatives basically is connected to curvature, right? And also I think the work that developed the second order calculus for this in some sense preceded this Olivier paper. And I think the Olivier paper is different, but was at least strongly inspired by these developments.
It would make sense.
Yeah, and so again, as a cartoon, we would look at gradient flow on a Riemannian manifold. So we would say something like this. If you feel a little bit uncomfortable with Riemannian geometry, it doesn't really, you can think about RD, right? So we've got just the usual gradient, f is just a function on RD, and maybe we think of a convex f on RD, and let's say without loss of generality, f will have a minimum at 0. And we want to know how fast this will converge. And of course, this is interesting to look at because there's lots of theory about optimization. And if we can understand well the theory of optimization, we can maybe do it like using these correspondences to do something for sampling. Because we think of sampling just as optimization on this probability manifold. And what is interesting here is that, or what kind of makes sense is if it's more convex, this f, then this will converge faster. So we can write like this. So the following holds. Let's say, okay, the following are equivalent, right? Oh, I'm gonna write quickly equivalent. So the Hessian of f is bounded below by the Riemannian tensor. It's just that this just means in RD, it means that the lowest eigenvalue of the Hessian is at least lambda. Right, so this is a convexity requirement on f. We can look at geodesics. So in RD, these are straight lines. And we look at the second derivative of this f along geodesics. If it's bounded below by lambda, that's an equivalent way of producing the Hessian. So the good thing about this is that essentially from this characterization, we can compute the Hessian. Right, so this is good because this is a little bit more friendly for this. And so this is just, so these are equivalences, but this is also this is good because it generalizes the notion of convexity from RD to Riemannian manifolds. So we have convexity in RD. We can say, okay, we take second derivatives and look at the lowest eigenvalue. But we can also say we look at straight lines, differentiate second 2 times along straight lines. But this can be directly put onto Riemannian manifolds because we just replace straight lines by geodesics and that's it. Right? So that's why it's nice to have this. And if we have this, so if 1, 2 holds, then we get 3 things. Okay. So if this f, which defines the gradient flow, which defines the valley in which the gradient flow goes, if this is convex with constant lambda, so it's at least as convex as lambda over 2 times x squared, right? Then the decay will be at least with this rate. So we match the rate and the convexity constant. And if it's more convex, then it will slide down faster the valley. Right? And we can have similar things. So the same basically holds true for the gradient. And also for the distance. So we've got basically 3 times the Satan decay estimates. One for just differing how we measure this decay. We can measure the decay in terms of the function that we're trying to optimize, or in terms of the gradient of the function that we're trying to optimize, or in terms of the distance of the point where we are to where we want to be. In terms of this distance, Riemannian distance, in RD this would be just the absolute value, or the what's it called? The Euclidean distance, right? Okay, so this is kind of the sketch. What does the time say? So that's kind of what you can say in Riemannian geometry and optimization, and you can say more. And I think it's kind of an interesting direction, trying to somehow get a bit more out of this and then translate it to this measure setting. So going from here to the measure setting, let's just consider the usual Fokker-Planck equation, which is gradient flow of the KL divergence. So then this F would be KL, right? Because we're considering gradient flow of the KL divergence. So we get here decay of the KL divergence along the solution of the Fokker-Planck equation. If we can prove with convexity, say it like this. This will turn out to be the Fisher information, and this will turn out to be the Wasserstein distance, because dg is the Wasserstein distance, right, according to this. So this is also d, this is the Riemannian distance. So these are the nice estimates, and then so we are left with trying to establish this. And the way this is done is sort of by direct computation. The problem is here we need to identify unit speed geodesics. So we haven't talked much about geodesics, but these are the minimizers of this. And so, okay, here I have to cut short, right? But you can show, like in Riemannian geometry, that minimizers of this functional satisfy a system of equations. So one optimality condition we already had. One optimality condition is that V is in fact a gradient. So this is just a restatement of this. Optimality conditions of this functional It's basically sort of you set the first derivation of this to 0, and then you get what are the optimality conditions. I mean, it's not that easy. So, but you have to use Lagrange multipliers to enforce this constraint. And the second one is this. It's cool because it's a Hamilton-Jacobi type equation, because you've got so if you've got a square and a gradient, it's an optimal control type of PDE. So we got a continuity equation, we've got a control type of equation, and so these together they describe minimizers or optimizers of this. And yeah, this is so this is kind of what I wanted to answer about this. What you said about other formulations. This can be seen as some sort of a continuous dual of the usual Wasserstein distance. Because if you go through, so if you try to derive this, which I kind of had planned to do, but if we try to derive this, then we would replace this by a Lagrange multiplier. And then using duality, we kind of get you a dual formulation involving these equations. And in fact, in the usual Wasserstein setting, you can kind of solve this and get a nice duality result. And for more general, like if you modify this, you can still get modified geodesic equations like this, but maybe it doesn't help either. So, but, I mean, it's not that explicit. Right? Okay.
Computationally, which perspective is more advantageous as well?
Computationally? You mean pen and paper computationally?
I was thinking it was like actually computing computer something.
I think solving this in general is tough.
Is one easier to solve than the other?
What are the options? What are the options on comparing between them?
I mean, solving this directly computationally is, I think, difficult. So, I mean, there's, for example, in when you look at regularized optimal transport, like Schrödinger bridges and stuff like this, then you can, that's basically replacing this by a noisy version. If you add something like this, then you get to a Schrödinger type of stuff. So you're replacing the continuity equation by some Fokker-Planck equation with noise. And there are some works trying to use this, like just trying to minimize this using neural networks. And I think this kind of makes sense. And there's also some works trying to do it with this. So there you also get, in the Schrödinger bridge stuff, you get also something like this as an optimality condition. And both are, I guess, possible. So I'm not sure what is better. Yeah. So to conclude, yeah, it's a long calculation, but you can actually do this calculation, right? So you can write down KL of rho pi. I'm just going to illustrate one term, okay? So it looks like this. Then now we think we look along geodesics, so along minimizers of this. So I just assume these two equations, and I just take two time derivatives here. So I do like this. Now here, I'm going to use the equation. And then I take a second derivative. Then the derivative falls on the rho and on the phi. And I use the equation again. And I do this, and it's a bit long, and but can write down the final result. So it looks like this. This term then you can then drop. This is a contribution from the underlying Riemannian manifold, so maybe it's 0. It's a Ricci curvature of the underlying Riemannian manifold. You can say it's 0 if you want to do RD. And then we just get the Hessian of V. So from this, we get that the Fokker-Planck equation decays in these ways if the Hessian of V is bounded below by a constant lambda, which is which I guess Sam showed in an easier way using couplings somehow. I mean, but
Yeah, I think you get more with this stuff.
yeah. So I kind of wanted to show this because yeah, and maybe as a last, yeah. I don't know. I'm just going to stop. So yeah.
Thanks a lot.
Yeah. Thanks. Yeah, so I tried to do this for this Stein thing, and somehow the expression is difficult. And so then what I did is about I said I replace. So you should do this for all rows, and I sort of just plugged for row. I put pi. So this means I compute just the curvature around the locally, right? And this gives them something. So then you can look at the kernel, how you should choose the kernel. And I had hoped that somehow I could say more by looking at this, right? But I mean, in general, it's kind of so. In general, so you can also do it for Kalman and stuff, but it's not clear that you can understand this expression very well. But you can do it. You just, yeah.
Okay, so it's right at the expression at the end.
Yeah, it's good. Yeah, you can definitely follow until here, and then it's maybe difficult, but yeah. But it might be interesting to look at it, yeah. So I don't think for the Kalman, for example, this has been done, but I kind of confident that it's just doing everything again, yeah.
And that being difficult at the end, do you think that just because it's hard to work this, or could it just not be, that convex?
Yeah, so for the Stein thing, it turned out just not being very convex. It's also like it's a very strong assumption here, right? So you say you are sort of convex in every direction, but what in fact you need is more of this. What is it? Like this kind of thing, right? What is it called if you've got a gradient flow like this? You can look at this. And then if you can bound this above by f of xt, then you can do Gronwall, right?
Yeah.
And so, but this is in some sense a much weaker condition than the Hessian, because you're basically just looking at the curvature in the direction where you actually go. And so, and this corresponds to the log-Sobolev inequality, if you translate it into this picture.
Yeah, that's what we did for PGD.
Right. Right. So if you're happy to assume log-Sobolev on the target, and you kind of do this, then you should be able to get exponential decay of these forms, I think. I mean, depending on the details, but yeah.
So, like in practice, like we're like in the situation where we're only interested where the starting endpoint are fixed. Do we really need all of the geodesics to satisfy this?
So again, if you
It's like asking for every geodesic to satisfy that seems quite
yeah, that's tough. Yeah,
like
yeah.
superfluous, right? Because we really only care about a limited.
I agree. Yeah, but I mean, this goes a little bit in this direction. So this is a weaker, considerably weaker condition. So log-Sobolev inequality. So one thing that you can do, for example, is like you do this. Like you first assume a convex bound on the Hessian. Then you get, then from this, you get a log-Sobolev inequality, this sort of Bakry-Emery condition. And then you can say, if you perturb the potential by a bounded function, then you still remain, then you can still have this inequality, but it gets exponentially worse in the oscillation of your perturbation. So, but this, I mean, this just shows that the log-Sobolev inequality holds a much greater generality. But I mean, you're completely right. I mean, it's a, I mean, it's definitely a good idea to relax this, but I'm not sure it's clear exactly how.
Do we actually see these types of convergence rates in practice?
Yeah. So this, I mean, I don't know in practice. Yeah, if you run like a Euler chain on a convex target, then I think you can see this convergence rate, right? If you look at maybe asymptotic variance, which is not the same, but which is related. Or what else would you look at? It's difficult to measure rate of convergence in MCMC, right? In some sense, but
yeah, I think in those strong cases where you can do the complement direction, that's it's not a proof, but it's quite tangible. There's a contracting, for example.
Yeah.
I can't remember if we do that. It's probably in one of like those moves or newspaper or something. Like for the PGD slight variant of this, bound the Federic pattern and stuff, you can see the exponential convergence. I think with the same lambda, the bound on the potential in terms of convexity.
So if you actually do like the log plot, you would actually see the same slope as that. Could you like numerically actually like approximate like the curvature? Like if I know the curvature, can I say something like this? I mean, if I don't know.
I don't know if you can squint eyeball. I try to eyeball. I always spend enough time squinting at tables and plots.
But I think, yeah, I mean, I think this is, I mean, I think these rates are somehow observable or relevant. Yeah, I think so.
Do you have any intuition how these things will work in multimodal settings where you don't have convexity?
I mean, some other technique is not very well adapted, I think, to this. No, I mean, I don't. I mean, I think it's an interesting perspective and so on, also for other reasons, because you can look at these geodesic equations and so on, and think like this, and maybe also, I mean, there are works that also like connect optimization to sampling in other ways. So if you maybe if you do subsampling and stuff like this, or like like mirror descent and stuff like this, I think it's interesting to try and import some of the techniques from optimization through this lens. But this particular calculation, I think, uses convexity quite a lot. And so curvature, in some sense, what Sam, I mean, it's not clear how this is directly related, right? I think it's more like in spirit related. It's not really the same, or there's no clear, very clear connection, at least, I think.
It depends how far you want to, like you're saying, you have the perturbation result, say, like, you're not, fail to be convex in a certain region, but it's,
yeah.
You can do things where, like, because everything's extremely explicit in one dimension, you can write down for yourself what the optimal transport map between a Gaussian and a mixture of two Gaussians looks like, and that will tell you many of the things you're interested in. So you'll see that the Lipschitz constant will blow up in the bit where it has to split the mass and so on. Here I would guess that the phi probably becomes quite irregular at some stages.
Yeah, this makes sense. Yeah.
reference to LinkedIn stuff?
For this stuff, it's so originally it's in if you just put in Otto Villani, this is going to be the first paper. It's sort of famous paper. It is called Talagrand. It has a kind of a mysterious title with Talagrand in the name, something like this. And they go far beyond this because they use it to prove other functional inequalities and stuff like this. And I mean, this is definitely the original paper. And so the books by Villani cover this in quite a lot of detail, right? So, yeah. So both books, right? There's topics in optimal transportation and optimal transport old and new, and they both cover this, I think. And yeah.
Okay. Then shall we close the day? So before leaving, so Nick, you're leaving today? Or?
Yeah.
Okay, so maybe it's a good moment to thank all the speakers because tomorrow you won't be here.
Thank you.
Personally, was really impressed by the quality of lectures. I'm really happy. Also, I would like to thank all the grant cosines and base squared for supporting this masterclass. The secretary that helped me with booking the hotel and everything, organization stuff, and Sam, which really helped me to organize this masterclass. Also, I think we should deserve a. And yeah, so for people that are within the grants, maybe we should discuss about the next masterclass.
So we were chatting, we'll do that at Brentwood so that Filippo and Lorenzo can join.
Okay. Yeah. For last time, I think it's tradition to invite the speakers for the next masterclass. So when we will figure out the topic and the dates, etc., we will let you know in case you are interested. Yes, that's it. For people that are joining for dinner, 7 p.m. at Radcliffe as usual. Yeah.
Should also thank Sebastian for putting all this.
Yes.
Yeah, I think so. Just so people can
Okay.
I think it's best to do it sooner so people can take a break before dinner.
As opposed to taking a break now and then having it.
Yeah, and then having another break. I think.
I suspect the answer is going to be negative, but during the Ambrosio textbook, they have kind of this notion of like, this is kind of how they define the Lachstein gradient is kind of in this sense. That's what I was looking for, was kind of a way to extend this definition to like the Stein geometry. But I think based on what you were saying, it feels like it's not going to be possible, right? Because somehow it's in terms of this global picture of Lachstein distance.
It's like so complicated.
So somehow, right, T here is the optimal. I guess they're assuming somehow existence on the optimal map between mu and nu.
Yeah, so that, yeah.
I guess there's not going to be a natural way to like, not even clear what that means, right, in this kind of setting.
At least to me, it's not clear.
Right.
So,
That's a shame.
Yeah.
It is right, because somehow like.
But
because somehow in the.
But having said this, I mean, you can. I mean, okay. But go ahead, yeah.
So somehow in the. So somehow when you're functional with lambda convex, you get this like kind of nice inequality.
Yeah.
And somehow the stuff I'm doing like relies quite high because his kind of like the above the tangent line type thing somehow. Essentially what I'm doing depends quite heavily on